Hello everyone, and welcome to the main talk, where we present our work, Efficient Binary Level Coverage Analysis. Our work starts from the premise that code coverage matters. Coverage reports are regularly used by software engineers, as well as project managers. They are needed to gain better insights into the health of their code base, and generally to inspire confidence in software. In addition to inspiring confidence, sometimes we simply have to track code coverage in order to comply with regulations, especially in safety-critical domains. More recently, code coverage was remarkably effective as a feedback signal in fuzzing. Having motivated our problem, we move now to look at how we track code coverage in practice. The current workflow typically starts from compiling the program using special compiler flags. Then we have to run the resulting binary to generate a dump file, which we use to report code coverage. There are two main issues with this flow. First, we need to compile the program, which may take a lot of time. More importantly, coverage instrumentation can conflict with compiler optimizations, which may lead to test regressions. So why not simplify things by starting directly from the binary? This would allow us to obtain a precise coverage report, regardless of the optimization level, used compiler, and even the programming language. Statement coverage is the most popular coverage metric. It can be easily supported by a binary coverage tool using off-the-shelf debug information to map instructions to lines of code. However, binary coverage can offer more detailed information. This includes insights about the individual branch decisions taken by the program. Flexibility is another advantage of binary coverage. It enables us to instrument only what's needed, like only one function instead of the whole program. Oftentimes, we want to track only what was changed in a recent commit. This flexibility can make a big difference in a continuous integration environment, where we might have tens of commits per day to our code base. We introduced bcov, which is a coverage analysis tool for x64 binaries. bcov statically instruments ELF binaries without compiler support. It starts by patching the binary, where it inserts two additional ELF segments. One segment is used for trampoline code, and the other segment stores coverage data. Then the user should run the binary along with our small runtime library, bcov-rt. Our library dumps the coverage data segment, which can later be used to report coverage. Our basic mechanism is to insert detours in targeted code locations to track basic block coverage. For example, assume we have the sequence of original instructions on the left. bcov would transform it to the following alternative sequence. The inserted detour will target a corresponding trampoline. In the trampoline, coverage data will first be updated using a single move instruction. Then, the relocated original instruction will be executed. And finally, control flow will be restored back to its original state. Note that bcov does not modify the stack, heap, nor any general purpose register. In other words, instrumentation is completely transparent. While the basic mechanism might be simple, there are lots of details involved to make it work in practice. Therefore, bcov combines many techniques to achieve efficiency, precision, and transparent instrumentation. Due to the short time available, we focus in the rest of the talk on the following contributions, which we consider to be the highlights of this work. The first is the pruning technique previously proposed by Agrawal in his POPL 94 paper. We choose this technique because of the superior efficiency and flexibility it provides compared to alternatives. Also, we propose a novel and a highly precise jump table analysis. It combines backward program slicing with microexecution. Hence, we simply called it sliced microexecution. The final technique is detour hosting. Variable length ISAs, such as x86, allow basic blocks to be smaller than the size of a detour, which is 5 bytes. Skipping such small basic blocks will incur a loss in the accuracy of the coverage reported by our tool. To address this problem, we try to choose a host for the detour among the neighboring basic blocks. We try to make this choice optimal using a greedy algorithm. Instrumenting all basic blocks would be highly inefficient. Instead, and by leveraging dominance relationships between basic blocks, we can drastically reduce the number of the required probes. Agrawal's probe pruning technique works in several steps. Basically, we have to recover the pre-dominator and the post-dominator trees, and then we merge them in a dominator graph. Later, we can build the superblock dominator graph that is shown in our example. bcov offers two instrumentation policies based on this graph. In the leaf node policy, we instrument only the leaves. Covering all leaf nodes implies that we have reached 100% coverage. However, the leaf node policy might not be precise enough. For example, it's possible to visit the node C without visiting D. This means that the coverage report might miss A and C even after visiting them. Therefore, we implement the any node policy, where we identify superblocks that are critical. In our example, the superblock AC is critical, which means that either A or C must be instrumented in order to track coverage without data loss. Consider the indirect jump instruction shown in this example, which represents a jump table. Our goal is to precisely recover its control flow targets. This is important because instrumentation decisions in bcov depend on the precision of the recovered control flow graph. In fact, instrumentation errors can break the binary, so high precision is important. We propose sliced microexecution as a precise and robust method for jump table analysis. It combines backward program slicing with microexecution. Microexecution is simply the ability to run any code fragment automatically. We use this novel combination to answer or falsify a series of hypotheses about each indirect jump. The first question is whether the jump table depends on a constant base address. By following the dependencies using backward slicing, we can see that the base address of the jump table is constant. As a result, this table depends on one variable only, which is the index. We come to the second question. Does this jump table have a bound condition? We know that jump tables are typically bounded because they are compiled from switch statements in C and C++. An out-of-bound index must be redirected to the default case of the switch statement. Again, and by using backward slicing, we find that the index value in the register R12B also influences the bound condition. So this answers our original question, and we now have a bound condition for this jump table. So far, we have identified the index of the table and the bound condition. The bound constant in our example is 5b. Now, we turn to microexecution to check that this sequence of instructions represents a jump table. To do this, we execute the slice while assigning different values to the index in the register R12B. We also check the behavior of the slice along the way. For values in the range below the bound constant, the jump table must be reachable, and the target should be a basic block within the same function. However, for values above the bound constant, the jump table must not be reachable. In other words, the bound condition must redirect the control flow to the default case of the switch statement. The size of basic blocks in x86 can be smaller than 5 bytes. In such a case, we cannot directly insert a detour. For example, we cannot insert a detour in place of this call instruction without overwriting the next basic block. Skipping small basic blocks might be an option. However, it will cause a loss in coverage accuracy. The loss can be high depending on the number of dominators in the superblock dominator graph. So what can we do? We know for sure that we should avoid relocating the entire function to a larger area where we can inline coverage update code. Also, we want to avoid using the int3 instruction, which is a 1-byte instruction used by debuggers to raise software interrupts. It's simply too costly. Our method is detour hosting, where for a group of guests and a group of suitable hosts, we try to find an optimal mapping between them using a greedy algorithm. For the sake of example, let us assume that we have found a host for this particular code instruction. bcov will generate the following patch. Now we are using a 2-byte jump instruction instead of the usual 5-byte detour. This short jump will target the detour hosted in the neighboring basic block. Note that padding bytes were overwritten in the process. The call detour will target the trampoline, where coverage data will be updated as usual. However, we now have to adjust the return address to match the one of the original binary. Finally, the original call instruction is rewritten to a jump instruction with the same effect. In this way, detour hosting allowed us to reuse the space already available in the binary, without a significant increase in the overhead. We extensively experimented with bcov, using a variety of binaries, compilers, and optimization levels. In total, we used bcov to instrument 95 binaries, which contain over 1.6 million functions. Note that all of our subjects are popular and well-tested. To give an impression about the size of our subjects, we compare them with the ubiquitous object-dump utility. An important thing to note here is that bcov can efficiently scale to large binaries. For example, it can patch our largest subject, LLC, in 30 seconds on a regular PC. Additionally, instrumentation is completely transparent. It does not introduce any test regressions. We measure the performance overhead introduced by our instrumentation by replacing original binaries with instrumented versions. Then, we rerun the entire test suite. While the overhead can be more than 30% for some binaries, it can also be as low as 1% for others. The overhead depends on different factors, like binary size and the lifetime of individual tests. For example, spawning many tests within a short period of time can increase the overhead, because a large amount of coverage data need to be written to the hard disk. Despite this, the average performance overhead of bcov stands at 14%, which is relatively low. We are not aware of any static instrumentation tool with functionality comparable to that of bcov. Therefore, we compare the performance overhead of bcov to the leading dynamic binary instrumentation tools, PIN and DynamoRail. First, we measure the overhead of the DBI tools without enabling any clients. Then, we enable drcov, which is the coverage analysis client of DynamoRail. The difference between the tools and bcov is quite large. For example, drcov has an average overhead of 730%. Additionally, it failed on the Python and Perl test suites. This demonstrates that the advantages offered by bcov are substantial, and they go well beyond efficiency to usability and transparency. We use the coverage analysis client drcov to measure the accuracy of the coverage reported by bcov. Our initial idea is to run a binary twice using the same input and then compare the reported coverage. However, we soon discovered that this was not such a good idea because our subjects feature non-deterministic behavior. Therefore, we came up with a different solution, where we trace a binary that is already instrumented by bcov. This solved the issue and allowed us to reliably compare both reports at basic block level. On this basis, the basic blocks reported by bcov can be classified to true positives, false positives, and false negatives. Note that the true negative category is not applicable to our settings, since drcov reports basic blocks that are not tracked by our tool. For example, basic blocks in the libc library. We first describe the subjects used in this experiment. They are compiled using GCC7 in a release build. The table shows only the subjects that drcov managed to run successfully. We also show the number of processes spawned during testing. This number has a direct effect on the size of coverage data, since new data is dumped at the shutdown of each process. drcov dumps a dynamic trace that can be small for short tests. On the other hand, bcov dumps coverage data that has a constant size, which depends on the size of the binary. Despite this, the size of the data dumped by bcov is comparable to that of a dynamic tracing tool like drcov. This table shows our accuracy results. The average and maximum number of true positives is shown for basic blocks as well as for instructions. The standard precision and recall metrics account for false positives and false negatives, respectively. The key result is that bcov is highly accurate, without a significant variance across all subjects. To conclude, after more than 20 years since the introduction of Dynest, we believe that it's time to revisit the trade-offs in trampoline-based instrumentation. Therefore, we implemented bcov from scratch in more than 17,000 lines of code. Of course, we had to skip a lot of details in this talk. These details are available in our paper and the experimental dataset. Also, bcov is open source, so we invite you to try it out. If you have any questions or comments, please reach out on GitHub, Reddit, or directly per email. We would be very happy to hear from you. Thank you.